Right now, somewhere above your head, there's a spot of sky so small that a single grain of sand, held at arm's length, could blot it out entirely. And tucked inside that impossibly tiny patch of darkness sits a faint reddish speck that, by all rights, shouldn't be there at all. If you saw it in raw telescope data without context, you'd probably assume it was a glitch, a stray pixel, a smudge on the sensor, the kind of noise that gets deleted without a second thought. But this one isn't noise, it's real. It's been checked, rechecked, and confirmed by instruments built specifically to catch light this faint and this old. And that confirmation has quietly forced some of the sharpest minds in astrophysics to admit something uncomfortable, the story we've been telling ourselves about how the early universe came together might be missing a piece. Stay with me through this video, because by the end you'll understand exactly why a team of respected scientists looked at this single dim object and essentially said, "We don't fully understand what we're seeing." That object now has a name, MOMZ14, and the tale of how it turned up and what it might be telling us is one of the strangest developments to come out of space science in years. Let's start with something you need to really sit with, just how ancient this particular beam of light actually is. It left its home galaxy around 13.5 billion years ago. For scale, the entire universe is only about 8 billion years old, so this light has been in transit for almost the whole of cosmic history. The entire time it traveled, the space it was moving through was stretching and expanding beneath it, and that stretching dragged its color further and further toward the red end of the spectrum. Then past red into the infrared, by the time it finally struck the massive gold-plated mirrors of the James Webb Space Telescope, it barely resembled visible light anymore. And when researchers finally pinned down and measured that light with precision, they hit a wall. The galaxy it came from is too bright for its size, too small to be putting out that much energy. And chemically, it looks far too developed, like a galaxy that had already been running for ages at a point in the universe's life when almost nothing should have existed yet. To grasp why that's such a big deal, you have to picture what the universe looked like before there was anything worth pointing a telescope at. Light moves at roughly 300 kilometers every second, the fastest speed anything can travel. But the universe is so staggeringly vast that a single photon can spend more time in transit than our entire planet has existed. For the first few 100 million years after the Big Bang, there was simply nothing to see. No stars, no galaxies, no planets, no chemistry to speak of, just a thick, dim haze of hydrogen and helium gas drifting outward into blackness. Scientists have a name for this stretch of time, the cosmic dark ages, and it's not just a dramatic label, it's a literal description. The gas was so dense that light physically could not travel through it. Even if you'd been floating in the middle of it with your eyes open, you'd have seen nothing but darkness in every direction. Eventually, gravity did what gravity always does. It pulled things together. Denser clumps of gas drew in more material, collapsed further, heated up, and eventually flared to life as the very first stars the universe had ever produced. These weren't calm, well-mannered stars like our sun. They were monstrous, violent, and short-lived, and their radiation ripped through the surrounding hydrogen fog, carving out clear bubbles of space. Those bubbles spread and merged until, at last, the fog began to lift for good. A turning point scientists call reionization, or the cosmic dawn. And this is exactly what makes MOMZ14 so important. It's a direct signal from right around that dawn, a chance to actually see the moment the universe first lit up. In the next part, we'll dig into exactly how astronomers pinned down its age, why it broke every previous distance record, and why its very existence has scientists rethinking timelines they thought were settled. Until fairly recently, the record for the most distant confirmed galaxy ever spotted belonged to an object called JADES, GSC-14, another find pulled from Webb's growing catalog of deep field images, Its redshift measured out at 14, 18. Now, redshift is essentially a cosmic stopwatch. It tells you how much the ongoing stretching of space has pulled a light wave toward the red end of the spectrum during its journey, and the higher that number climbs, the older and more distant the light actually is. A redshift of 14. 18 meant the light scientists were staring at had left its source when the universe was only around 290 million years old. Even by the standards of cutting-edge astronomy that already sat right at the outer edge of what anyone expected to find. Then a team working out of the Kavli Institute at MIT decided to do something clever. Instead of chasing brand new observations, they went back through imaging data Webb had already collected, hunting specifically for promising candidates that might have slipped past other researchers too quickly. Buried in that old data, they found something odd, an object that lit up clearly at longer infrared wavelengths but essentially disappeared at shorter ones. That's precisely the fingerprint you'd expect from light that's been redshifted so severely that its entire blue end has effectively been erased. That pattern alone was enough to justify spending valuable telescope time chasing it down properly. So in the spring of 2025, the team pointed Webb directly at the object and ran its light through an instrument called an IR spec, which splits incoming light into its individual wavelengths, much like a glass prism breaking sunlight into a rainbow. That's the moment scientists stop guessing and start measuring with real precision. When the spectrum came back, it confirmed a redshift of 14, 44. They named the object MOMZ14, and with that single confirmed measurement, the previous distance record was broken. This is light that left its galaxy roughly 280 million years after the Big Bang, a point when the universe had lived through barely 2% of its entire existence so far. Let's actually try to picture what that means. Imagine squeezing the entire history of the universe into a single calendar year. The Big Bang happens in the very first instant of January 1st. This galaxy is already shining by around January 7th. The dinosaurs don't show up until the day after Christmas. Every human being who has ever lived fits entirely into the last few minutes before midnight on New Year's Eve. And somehow we built a machine, flung it roughly 1.5 million kilometers from Earth, and managed to catch a single particle of light from the very first week of January. Here's exactly where the real trouble starts. MOMZ14 is tiny. Its visible light spans something like 240 light years across. For comparison, our own Milky Way stretches about 100 light years from edge to edge, meaning this object is literally hundreds of times more compact than the galaxy we call home. In scale, it's closer to a single dense star cluster than to anything we'd normally call a full galaxy. And despite being so small, it's absurdly bright. Pound for pound, this object is pumping out far more light than anything that young and that compact has any business producing, according to every model we currently rely on. Standard formation theory says early galaxies at this stage of cosmic history should look dim, messy, and slow to come together. This one looks compact, mature, and intensely energetic instead, almost as if it skipped several stages of normal galactic development entirely. So what could possibly be powering something like this? Scientists have floated a few different explanations, and every single one of them comes loaded with uncomfortable implications for how we think the universe actually works. In the next part, we'll walk through exactly what those explanations are, and why the strangest detail in this whole discovery isn't even the brightness. One possibility is that star formation in the extremely early universe was simply far more efficient than anyone assumed, with gas collapsing into new stars unusually fast, and with almost none of the sluggishness we see in galaxies today. Another possibility is that the very first generation of stars ever formed were so massive and so blisteringly hot that even a small number of them could outshine an entire modern galaxy on their own. And a third possibility is that something else entirely is feeding at the center of this object, potentially an extremely early black hole, actively pulling in surrounding material and blasting out enormous amounts of energy in the process. Every one of these explanations would force scientists to seriously rewrite something fundamental about how they believed the early universe actually worked. But here's the twist. The brightness itself isn't even the strangest part of this discovery. When researchers dug deeper into the full spectrum of light coming from this galaxy, they found something in the surrounding gas, a specific chemical signature involving the ratio between nitrogen and carbon, and that ratio came back unusually, almost impossibly high. This detail matters enormously because heavier chemical elements are never free. The universe began with almost nothing but hydrogen, helium, and a faint trace of lithium. Every other element in existence, the carbon inside every living cell, the nitrogen woven into every strand of DNA, even the oxygen you're breathing right now, had to be forged inside the cores of stars first, then violently scattered back into space when those stars eventually died. Building up a genuinely enriched chemical environment inside a galaxy takes multiple full generations of stars living, dying, and recycling their material. At only 280 million years old, there should have barely been enough time for a single generation of stars to complete that entire cycle, let alone enough stacked generations to explain the chemical imbalance researchers actually found here. And there's a second, equally strange layer buried in this same finding. That exact nitrogen-rich signature has also shown up somewhere much closer to home, inside structures called globular clusters, extremely dense, ancient spherical collections holding hundreds of thousands of stars, typically found orbiting the outer edges of galaxies like our own Milky Way. For a long time, these clusters have been treated as leftover relics from somewhere within the first few billion years of cosmic history. If MZ14 is already showing that exact same chemical fingerprint, it suggests that whatever process builds structures like globular clusters may have kicked into gear almost the moment the early cosmic fog cleared. That doesn't just nudge our existing timeline slightly earlier. It genuinely compresses it in a way that's hard to fully explain. At this point, you might reasonably think, fine, this is one strange, unusual object, and science produces outliers sometimes. Except this isn't an isolated case tucked away in some corner of the data. Ever since the James Webb Space Telescope became fully operational back in 2022, it has been delivering some version of this exact same surprising result again and again. Galaxy after galaxy, spotted deep in the early universe, keeps turning out too luminous, too developed, too chemically enriched, and too structurally organized for the specific moment in cosmic history we're catching it in. What researchers originally expected to be a small handful of rare exceptions has quietly, steadily become something that looks a lot more like the standard result. This matters enormously because our current framework for how large-scale cosmic structure assembles over time wasn't sketched out casually. It represents decades of careful observation, detailed simulation work, and repeated testing, and it has genuinely held up under an enormous number of those tests. That framework isn't simply wrong. But it does keep getting surprised again and again in this exact same direction, and a model that keeps getting surprised consistently in the same direction is a model that almost certainly has a genuine gap hiding somewhere inside it. In the next part, we'll get into the possible explanations scientists are now seriously entertaining, including one idea so strange it sounds like it belongs in science fiction rather than a peer-reviewed paper. Maybe dark matter played a far more aggressive role in seeding the earliest cosmic structures than current models have properly accounted for. Maybe the underlying physics governing that very first generation of stars is meaningfully different from anything sitting in our existing scientific catalog. Or maybe there's some entirely unknown mechanism operating during those first 100 million years of cosmic history that scientists simply haven't identified yet. None of that means science has failed at its job. This is actually science doing exactly what it's supposed to do, running headfirst into a genuine wall of contradictory evidence, and refusing to look away or pretend the problem isn't there. And it's extremely likely this particular distance record won't stand for very long either. Researchers involved in the discovery have already said publicly that Webb appears fully capable of pushing this cosmic frontier back even further, potentially reaching redshifts that seemed completely unimaginable just a few years ago, edging ever closer to the era of the very first stars in the universe. There's also a completely separate, genuinely strange anomaly buried inside Webb's broader deep field data, and researchers are still actively debating whether it might somehow connect back to everything we've just covered. A separate group went through Webb's deep field images and sorted a large sample of spiral galaxies based purely on which direction their spiral arms wind, essentially telling you which way each galaxy is spinning. The resulting count came back noticeably lopsided. A clear majority of these galaxies appeared to be rotating in the same direction as one another. In a universe with no built-in preferred direction or orientation, that split should land close to an even 50-50, roughly half spinning one way and half the other. There's no obvious reason the wider cosmos should have a favorite rotational direction baked into it. The researchers behind that study raised a genuinely wild possibility to help explain it, one that honestly sounds more at home in a science fiction script than a peer-reviewed paper. What if that spinning imbalance is actually a kind of leftover residue from the specific conditions our own universe originally formed inside of? What if, in some very real physical sense, our entire observable universe is sitting inside something like a black hole? Stay with this for a moment, because it's more coherent as a scientific hypothesis than it might sound at first. When enough matter collapses under its own gravity, it eventually forms what's known as an event horizon, a boundary that not even light can climb back out from once it crosses over. Cross that line, and from the perspective of everyone standing outside it, you are permanently gone. What actually happens beyond that boundary remains genuinely unknown territory. Our current math simply hands us an undefined infinity and stops being useful right at that point. A concept called black hole cosmology takes that exact gap in our understanding and offers one possible way of filling it in. What if the interior of a black hole isn't a dead end at all, but a separate region of space that keeps expanding on its own? What if everything we currently call our observable universe is simply what the inside of a black hole actually looks like from within it? Now connect that back to the very beginning of everything. Our standard scientific account already describes the universe as having started from something called a singularity, an infinitely dense single point, which happens to be the exact same term scientists use for the theoretical center of a black hole. Under this interpretation, the Big Bang wasn't necessarily some explosive eruption into empty surrounding space. It may instead represent the far side of a gravitational collapse that happened somewhere else entirely, inside some larger parent universe, at a moment when enough matter fell together and sealed itself off behind its own event horizon. Coming up, we'll weigh this idea against the simpler, more grounded explanation scientists also take seriously, and land on what the honest, balanced takeaway from all of this actually is. I want to be genuinely fair and balanced here, because there's also a much simpler, more grounded explanation on the table, and intellectual honesty means giving it equal weight. That spinning direction imbalance could ultimately turn out to be nothing more than a measurement artifact. Our own Milky Way is constantly moving through space, and that motion can subtly brighten objects that happen to be rotating against our direction of travel, while slightly dimming objects rotating along with it. If our current estimate of the Milky Way's own motion turns out to be even a little off, that alone could introduce a real statistical bias into this data without requiring any deep cosmic mystery to explain it at all. That same healthy scientific caution applies just as strongly to MZ14 itself. Small sample sizes can genuinely mislead researchers. Early measurements sometimes